So hey guys, welcome to Chemistry of Carbon channel. This is Abhinav here, and today we are going to introduce the topic of carbon and its compounds. So hope everyone can hear me clearly. There's no lag in this audio. Okay, so today we are going to be looking at carbon and its compounds. So let's just get started right away. So just before we just dig into the topic, let's just learn something about carbon. So, carbon forms about 3 million compounds, which is more than the rest of the elements combined. It is so vast that there's a branch of chemistry dedicated to carbon called organic chemistry. Okay, so how? How does carbon form so many compounds? Just how? So, carbon is a tetravalent compound. It cannot gain or lose electrons, so it shares electrons. So if we have a carbon atom here, like right here, so if we had to add 4 electrons, like we would need so much energy, and on top of that, all the electrons in the outermost shell would anyways shield it from getting inside the shell. So this would mean that a little bit of energy is enough to remove the outermost electrons. So this is not stable. C4 minus is not stable. Okay. What about C4 plus? C4 plus. Well, if we had to remove electrons, we could remove one, two, and we could remove the third one with a lot of energy. But what about the fourth one? What about this? We would need so much energy because first of all, when we remove electrons, the shell keeps coming closer to the nucleus, and 6 protons would be applying a force on 3 electrons basically. It would be it would need tremendous amount of energy to just uproot that electron. So, and even if we do it, 2 electrons and 6 protons would be highly unstable. It would just explode. So that's too not possible. But what does it do then? So it shares electrons, yes, but what kind of a bond is it? This kind of a bond is known as covalent bond. So carbon shows a property known as catenation that allows it to form very large compounds. Catenation. In simple terms, carbon just bonds with itself. It's a self-linking property of carbon to form very large chains. And also carbon has a small atomic radius, so it can hold on to the electrons. Does not require a lot of energy. Covalent bond. What is a covalent bond? Let's just look at it in a little more simple terms. So a covalent bond is when two atoms or species share the electrons. They share it basically. Now let's take an example. Let's say we have Ram and Mohan. They have 2 electrons in the outermost shell. Let's say 6 electrons in the outermost shell for simplicity. Now, Ram and Mohan need 2 electrons to become stable. So, what will they do now? Will they give away the electrons? No, that's not possible because if Mohan gives the electrons to Ram, Mohan would not be able to achieve the octet, and same applies to Ram. So they share the electrons. So this kind of bonding is known as covalent bond. Let's take some examples to understand it better. CO2. Carbon has 2 double covalent bonds with oxygen. So oxygen shares 2 electrons in carbon, and on this side carbon shares 2 electrons with oxygen, and same here. Now, let's look at some important facts on carbon compounds or in general covalent compounds. So we have a table here on the melting and boiling points of some compounds of carbon. This is acetic acid or ethanoic acid. It has a melting point of 290 Kelvin, about 17 degrees centigrade, a boiling point of 391 Kelvin. Chloroform, which is generally prepared in laboratories, is having a slightly lower melting point and boiling point. Ethanol, which is C2H5OH or ethyl alcohol, has even lesser melting point and boiling point, is a little bit higher than chloroform. Methane, which is itself a gas, does not require much to melt because it's a gas basically. Its melting point is 90 Kelvin, which is less than the freezing point of ice, and its boiling point is also less than the freezing point of ice because it's already in gaseous state. Some important facts based on that, based on what we infer from the table, are most carbon compounds are poor conductors of electricity. Like, how is that possible? So basically, we see that the melting and boiling point of these compounds is less. So that means the electrostatic forces of attraction or the force of attraction will be less. It would not be so much. Now, basically when they share it, they are giving their electrons. So when we split the bonds, the electrons would basically just go back to the shells, right? This means that there's no free electron or there's no formation of ions when we break the bond. So basically it is a poor conductor of electricity, and since the compounds are largely non-conductors of electricity, you can conclude that the bonding in these compounds does not give rise to any ions. From the data given in table 4.1 on the boiling and melting points, the carbon compounds, we find that these compounds have low melting and boiling points. Yes, this, like, ionic compounds generally have a higher boiling, melting and boiling point than 1000 degrees centigrade, like sodium chloride. So the forces of attraction between the molecules are not very strong. In simple terms, these electrons are basically shared, right? So it's not like one of them is giving it or one of them is taking it. So it's like almost like they just want to share. They don't want to steal it or take, like, give it. Now, electron dot structure. So what is electron dot structure? So this is a way of representing atoms as molecules or bonded, or it can be just single atoms, monoatoms. So this is a way of representing their valence shells alone. It does not include the other shells. Now, this is the example of hydrogen atoms. This is how we draw two hydrogen atoms bonding, their electron dot structure. In simple terms, we can just say that a cross is for non-metals and the dot is for metals. Same goes for oxygen, which needs 2 electrons in the outermost shell, and nitrogen needs 3. But methane has a dot and a cross. Hydrogen and carbon are both non-metals. Why is that so? Because hydrogen has more properties of metals than carbon. It acts as metals and non-metals. That's why we represent it with a dot to show that it has more metallic properties, a metallic character than carbon. Now, what would be the electron dot structure for molecule of sulfur, which is made up of 8 atoms of sulfur, that is S8. It's also known as rhombic sulfur. So first we need to know the structure of sulfur. It looks like a crown. Yes, it looks like a crown. How we draw it? We could just draw it the same way as oxygen, because they both have 6 electrons in the outermost shell. Not drawing the electrons for those, but it's going to be the same way. So if we draw these kind of crosses and the circles for all sulfur atoms, this would be the electron dot structure of S8 or just sulfur molecule. Now, allotropes of carbon. Before we get into allotropes of carbon, we should just know that carbon has catenation, right? It bonds with itself. Now, if it bonds to itself, it will have the same chemical composition, yes, but carbon can bond like this with itself or it can just bond like this. So based on these physical properties may vary. There may be a change in the physical properties. So some of the examples of allotropes, as we call them, which are the same chemical composition but different physical properties, they are diamond, graphite, Buckminster fullerene, which belongs to the fullerene family, and amorphous carbon. We'll not look at amorphous carbon now. It's just a non-crystalline form of carbon, includes coal, soot, lamp black, carbon black, etc. It goes on. Now, we saw that the element carbon occurs in different forms in nature with widely varying physical properties. So both diamond and graphite are formed by carbon atoms. The difference lies in the way the carbon atoms are bonded to one another. Just like we saw, it can be like this, or carbon can be bonded like this. But let's look at graphite and diamond in more detail for now. In diamond, each carbon atom is bonded to 4 other carbon atoms, forming a rigid 3-dimensional structure. In graphite, each carbon atom is bonded to 3 other carbon atoms in the same plane, giving a hexagonal array. And they form layers basically in graphite. One of these bonds is a double bond, no, it's all single bonds, and thus the valency of the carbon is satisfied. In graphite, structures formed by the hexagonal arrays being placed in layers one over the other. In both graphite and diamond, there are all single bonds. These two different structures result in diamond and graphite having very different physical properties, even though their chemical properties are the same. Diamond is the hardest substance known, while graphite is smooth and slippery. Graphite is also a very good conductor of electricity, unlike other nonmetals. But what is the reason for that? We'll see it in how we represent diamond and graphite. This is how diamond and graphite looks. So we look at this atom, there are 4 bonds, and the same in this. So it's just the same in all the bonds, in all the atoms of carbon. Now, if we look at graphite, we see that there are 3 bonds. Yes. So it does not, it's not a full octet. So what happens to the 1 electron? This is free. This is a free electron. So this is what constitutes the charge of the electron, and this is how current flows through graphite. Now let's look at Buckminster fullerene. Buckminster fullerene has a formula C60. It looks like a football, and it was named so because it looked like one of the dome-like structures of a very famous architect, Buckminster Fuller. He was a genius. So that was all for the allotropes of carbon. Now let's look at organic compounds. Like, what is the origin of organic compounds and some small theories based on it. Organic compounds, the 2 characteristic features seen in carbon, that is tetravalency and catenation, put together rise in many compounds. Many have the same non-carbon atom or group of atoms attached to different carbon atoms. These compounds were initially extracted from natural substances, and it was thought that these carbon compounds or organic compounds could only be formed within a living system. That is, it was postulated that a vital force was necessary for their synthesis. But scientist Frederick Wohler disproved this in 1828 by preparing urea from ammonium cyanate. So this is ammonium cyanate. It was converted to urea, yes, which is the common name. But carbon compounds, except for carbides, oxides of carbon, carbonate, and hydrogen carbonate salts, continue to be studied under organic chemistry. This is because they don't show many properties that are shown by organic compounds. So that's all for today. We'll just practice some questions actually, and let's look at some electron dot structures of ethane and things like that. Now, ethane is has a formula C2H6. That means ethane would have a carbon bonded to itself, because otherwise it cannot be six hydrogens. Now it will have six hydrogens like this. So how would its electron dot structure be? It would be like this. C, and let's just draw C. And then this should be, we would have to draw the same way as methane with the hydrogen with the dot. It would take some time, but yes, this is the structure of, this is the electron dot structure of ethane. Now we'll just draw the circles for hydrogen and the two carbons. Now in this we have to ensure that the atom have the electrons encircled in them. Basically it has to be shared among, it has to cover all of them. It shouldn't be like only hydrogen has one part of it and carbon does not. So this is the electron dot structure of ethane. Now let's look at ethene. So it would have double bond like this in between, because it has a formula C2H4. So it will have double bond here and hydrogens here. But just for the electron dot structure, instead of doing it like this, we're going to do it like this. Okay, so now we saw that if this is like this, carbon would have electrons like this, so this would be 4. Now we can draw the dot and the hydrogen, dot and the hydrogen, dot and the hydrogen. Just, it would just be exactly symmetrical, because most organic compounds are symmetrical. So now if we draw hydrogen atoms like this, we have to note like this shouldn't intersect like this. Just yeah, because it's not that the atoms are. Now we have to draw the circle around carbon. It should be a proper circle, but yeah, this should suffice for the moment. So this is the electron dot structure of ethene, and the same goes for all organic compounds. So thank you guys, hope you guys enjoyed the session, and if you guys found the session helpful, do hit that like button, subscribe to the channel, and share this video with your friends and family so that they can be benefited from it, and do comment on the comment box below. Thank you.